Continuing on Physical Chemistry, Chapter 9, we're in Section 5 now. We're going to talk about ideal solutions in liquids or solids. For example, brass is a solid solution of copper and zinc. All alloys are actually solid solutions. For example, let's say we have material A and B. So there's an intermolecular force between A and A. There's also intermolecular force between B and B. And also between A and B. So if these are equal to each other, if the intermolecular attractions between A and B is the same as between B and A, then that's going to be an ideal solution. So this represents the intermolecular forces between those molecules. So like I said, if the intermolecular force between A and B is the same as the intermolecular force between A and A has the same structure as B, then the solution is an ideal solution. Now by structure we mean generally, like the size of the molecule and what type of geometry it has, etc. So for examples of ideal solutions, let's say we have iodomethane with carbon-12 and iodomethane with carbon-13. Now in this case we're going to say mu is the dipole moment, not the chemical potential or anything. Then we'll say, okay, the dipole moment of the iodomethane with carbon-12 is not really the same as the iodomethane with carbon-13, but it's pretty close. Slightly different. Okay, another example of an ideal solution would be, let's say we have benzene and toluene. Remember, toluene is just a methyl benzene. And then another example of an ideal solution, or pretty close to it, would be chloroethane and bromoethane. They're about the same size and shape, just slightly different. Okay, so we do get deviations from ideal solution behavior that are due to different possibilities. So one, if the intermolecular attractions between A and B and B are not the same as the intermolecular attractions from A and B. Like let's say if A is polar and B is nonpolar, then obviously it's not going to make an ideal solution. And likewise, let's say the size and the shape of substance A is not equal to the size and shape of B. Well, then that wouldn't be an ideal solution either. Now, if the molecules are different, then we have a non-ideal solution. An example I just gave you in a previous section was ethanol and water, since water is a lot more polar than ethanol, and it can hydrogen bond to itself, etc. Okay, so here's the question. What is the thermodynamic definition of an ideal solution? Because remember, in thermodynamics, we don't strictly talk about molecules. We just talk about macro properties. Okay, so from ideal solutions, the change in the Gibbs free energy of mixing is equal to the gas constant R times the absolute temperature times this quantity of the number of moles of substance A times the natural log of the mole fraction of substance A plus the number of moles of substance B times the natural log of the mole fraction of substance B. So like I said, chi or X is the mole fraction and N is the number of moles. Now the differential of the Gibbs free energy, remember, is minus entropy times the differential of temperature plus volume times the differential of pressure. So at constant temperature, we just get the differential of the Gibbs free energy is equal to volume times the differential of pressure. And then of course, if that would be roughly equal to volume times the change in pressure. Now the change in Gibbs free energy of mixing is not equal to 0. Even if you have an ideal solution and you're at constant temperature and pressure. The change in Gibbs free energy in mixing can be found from the vapor pressure measurements, experimentally obviously. The change in internal energy of mixing is equal to 0 because there's no change in intermolecular forces. The change in volume from mixing is equal to 0 since we said the molecules are about the same size and shape. So they should pack in together the same as they were separate. The change in enthalpy from mixing is going to be equal to the change in internal energy of mixing plus pressure times the change in volume from mixing. This is 0, therefore this is 0. But what about the change in enthalpy from mixing? Or not enthalpy, entropy of mixing. Well, we're going to have to figure out what it is, but we know it's not 0. The reason, of course, is going to be spontaneous. Okay, so let's say we have two liquids here, A and B. So state 1, we've got A and B in here separately. A is at whatever temperature and pressure. B is at the same temperature and pressure. We're going to allow them to mix. So state 2 is going to be the fully mixed state. We're going to have A and B in here mixed together, still at the same temperature and pressure. But remember, this is an ideal solution, so we're saying A and B are about the same size and shape. Now remember, the change in entropy from mixing is going to equal to state 2 minus state 1, and that's going to be equal to K, which is Boltzmann's constant, times the natural log of pressure 2 over pressure 1. Oh, probability, sorry. Probability of state 2 divided by the probability of state 1. Okay, so like I said, in this case, P is probability, not pressure. Got to be careful not to get those switched around. Okay, and again, star in this chapter means before mixing. So we have the volume of substance A unmixed divided by the volume, and that's equal to the volume of A mixed. It's going to be equal to the volume of A unmixed plus volume of B mixed. Now, V is the total volume in the mixture, and the reason we can add these is because it's an ideal solution. We said in a non-ideal solution you can't necessarily do this. So volume is equal to the unmixed volume if you have an ideal solution. That's why we were allowed to add that up. So the volume of A unmixed divided by the volume is equal to the volume of A unmixed divided by the volume of A plus the volume of B. So the volume of A unmixed divided by the volume, remember, is the probability that any given A is in the original part of the system before mixing, the left part for A. So the change in entropy from mixing is going to be the number of moles of substance A times R, gas constant, times the natural log of the volume divided by VA, and then the plus the number of moles of substance B times R times the natural log of the volume divided by the volume of B. This is for an ideal gas mixture. So the change in entropy from mixing is going to be minus NA R natural log of VA star over V. Notice how we flipped it upside down, this way we have a minus sign. Minus the number of moles of substance B times R times the natural log of the unmixed molar volume from B divided by the total volume. And that's an ideal solution or mixture. Now, since A and B form an ideal solution, we know that the molecules are the same size, they have the same shape, and they have roughly the same intermolecular forces. So, what that means is that the partial molar volume of A unmixed is equal to the partial, or just the molar volume of B unmixed. So we could use them interchangeably. So the VA star, the volume of A unmixed, is equal to the number of moles of substance A times the molar volume unmixed of substance A. And likewise, the volume of substance B unmixed is equal to the number of moles of substance B times the molar volume of B unmixed. So putting that back into the equation we had before, we get the volume is going to be equal to the volume of A unmixed plus the volume of B unmixed, which means we're going to have the number of moles of substance A plus B, we factor that out, times the partial molar volume of A unmixed. And that's going to be equal to the number of moles of substance A plus the number of moles of B times the molar volume of B unmixed. Either way, because we said they're the same. So the change in entropy from mixing is equal to minus R times this whole quantity, the number of moles of substance A times the natural log of mole fraction of A, plus the number of moles of substance B times the natural log of the mole fraction of B. And this is only for an ideal solution, and assuming we're still at constant temperature and pressure. So you'll notice this is similar to the equation we ended up with for mixing ideal gases. So the change in the entropy from mixing is equal to minus the number of moles of substance A times the gas constant R times the natural log of this whole quantity. The number of moles of substance A times the molar volume of A unmixed divided by the number of moles of A plus the number of moles of B times the molar volume unmixed of A minus the number of moles of B times R times the natural log of this whole quantity here, the number of moles of substance B times the molar volume of substance B unmixed, divided by the number of moles of substance A plus the number of moles of substance B times the molar volume of substance B. Now remember, The change in Gibbs free energy from mixing is going to be equal to the change in enthalpy from mixing minus temperature times the change in entropy from mixing. Now we said the change in enthalpy from mixing is equal to 0 for an ideal solution since the intermolecular forces are all the same. So whatever bonds we end up breaking forming the solution, we're going to end up forming similar bonds somewhere else. So the change in Gibbs free energy from mixing is going to be equal to 0 minus the temperature times this whole quantity minus Na times R times the natural log of mole fraction of A minus the number of moles of substance B times R times the natural log of mole fraction of substance B. That's for an ideal solution only, obviously. Now, the change in Gibbs free energy from mixing is going to be equal to R times the temperature times this whole quantity, number of moles of substance A times the natural log of the mole fraction of A, plus the number of moles of substance B times the natural log of the mole fraction of B. That's for an ideal solution. So in summation notation, we'll get the change in Gibbs free energy from mixing is equal to the gas constant R times the absolute temperature times the sum over all substances I times the number of moles of substance I times the natural log of the mole fraction of substance I. So like I said, R is Avogadro's number times Boltzmann constant. So R is equal to the number of moles of substance A times K. So remember, energy is in basically units energy per mole when we're talking about, macro quantity. K is more like energy per atom, so that's more for a microscopic quantity. So remember, the limit as pressure approaches 0 of PV over NT is equal to R. So mu sub I, now we're not talking about dipole moment, we're talking about the chemical potential again. And so mu subscript I is the chemical potential of substance I. Now the change in Gibbs free energy from mixing is going to be equal to Gibbs free energy minus the Gibbs free energy unmixed. Now for the pure substance, the molar Gibbs free energy of substance I is equal to the chemical potential I, which is the Gibbs free energy of substance I divided by the number of moles. Obviously that would be of the substance. And that's going to be equal to this molar Gibbs free energy of I. Now the Gibbs free energy is equal to summation notation of all the substances I, the number of moles of substances I, times the molar volume of substance I. Or partial molar volume. So the Gibbs free energy, this is the partial molar Gibbs energy. So G star, that's Gibbs free energy unmixed, is equal to the summation of over all substances I times the number of moles of substance I times the molar Gibbs free energy of substance I unmixed. So the unmixed chemical potential of substance I is equal to the molar Gibbs free energy of substance I when it's unmixed. So this gives us that the change in Gibbs free energy from mixing is equal to the Gibbs free energy minus Gibbs free energy star, so that means unmixed, and that's equal to the sum I over all substances I is implied there. The number of moles of substance I times the chemical potential of substance I, minus again the sum over all substance I is implied there. The number of moles of substance I times the unmixed chemical potential of substance I. And that's going to be equal to the gas constant R times temperature times the sum over all substances I times the number of moles of substances I times the natural log of the mole fraction of substance I. So we get RT times the sum over all substances I of the number of moles of substance I times the mole fraction of substance I, and that's equal to the sum over all substances I of the number of moles of substance I times the chemical potential of substance I, minus the sum of all the substances I, the number of moles of substance I times the chemical potential unmixed of substance I. So then we get the sum over all substances I, the number of moles of substance I, times chemical potential substance I, is equal to the sum over all substances I of the number of moles of substance I, times the chemical potential of substance I unmixed. Oops, where was I? Okay, plus RT times the sum over all substance I of the number of moles of substance I times the natural log of the mole fraction of substance I. And then we get the sum over all substance I of the number of moles of substance I times the chemical potential of substance I is equal to the sum over all substances I of the number of moles of substance I times this whole quantity, the chemical potential of substance I unmixed plus RT times the natural log of the mole fraction of substance I. Oops. So this only solution to this problem is if the chemical potential of substance I is equal to the chemical potential of substance I unmixed plus RT natural log of mole fraction of substance I. So then we have the chemical potential of substance I is equal to the chemical potential of substance I unmixed as a function of temperature plus R times the temperature times the natural log of mole fraction of Ki, the mole fraction of substance I. That's the ideal solution law. This equation here, this is the thermodynamic definition of an ideal solution. Now, a solution is ideal if the chemical potential of every single component in the solution obeys that equation for all solution compositions and for a range of temperature and pressure. Now, we always want to compare with PV equals nRT because that's an ideal gas. So real gases act like the ideal gases as either the pressure approaches zero or the density approaches zero. The concentration approaches zero. Now, RT, natural log of the mole fraction of substance I, is less than zero. So it's normally negative. So that means the chemical potential of substance I is less than the unmixed chemical potential of substance I. Now, chemical potential of substance I unmixed is constant, of course. That's given for any material. So here's a graph showing what is going on. So here's chemical potential of substance I, how it can be positive, negative, or zero. And here's the mole fraction. So at a really low mole fraction, we got a negative potential. As higher and higher mole fractions, eventually we're going to get to where the chemical potential is I. And then eventually we're going to get up to where you have the pure substance. And of course, the pure substance, then the chemical potential of substance I is equal to the unmixed chemical potential of substance I. But notice it's always lower. It's always down here. And of course, this graph is assuming temperature and pressure are constant. So what you should see here, as the mole fraction approaches zero, the chemical potential of substance I approaches negative infinity.